pleased to present our speaker today. It's Parker Fagrelius. She's a PhD graduate student at UC Berkeley. Her bachelor's degree in physics is from Dartmouth, where she was a mission manager for a student-run CubeSat program. She spent 4 years at the Jet Propulsion Laboratory as a systems engineer and then a project manager as part of the JPL Phaeton program, working on something I believe called OPALS, Optical Payload Lasercom Science. Yeah. But today she's here to discuss her work at Berkeley, which is a forerunner to a very large project indeed called DESI, where she was working on a, if it's a proof of concept or some, or a prototype of called ProtoDESI. Let's give a warm welcome to Parker Fagrelius.
Thank you very much for having me. It's great to be here. So I was just going to introduce myself, but you did a great job. Thank you very much. Again, my name's Parker. I'm currently a PhD student, probably have 2 or 3 years left. I work primarily at Lawrence Berkeley National Laboratory, which is up the hill from the campus. And I work with 2 people, one David Schlegel and the other Saul Perlmutter. Saul works on Type 1a supernova as a cosmology indicator, and David, my primary advisor, works on BAO, which I'll talk about a little bit more. This past year, I have been working on ProtoDESI, acting as a manager, not so much handling the budget, thank goodness, but just making sure that it gets done. So that's going to be the majority of this talk, is what ProtoDESI was and what we were able to accomplish. As Dr. Severson said, before coming to Berkeley, I went to Dartmouth and got a degree in physics. I took a year off. I was a bit bored of physics, I would say, in that I was tired of taking classes. So I went and taught physics, and it really kind of re-inspired me to go back and finish my degree, which was a good thing. And then after that, I was able to get a job at Jet Propulsion Lab. They were sponsoring our project at Dartmouth College. So I entered as a systems engineer, never having taken an engineering class in my life, but acting as a translator between scientists and engineers and helping them write requirements, because engineers speak a different language than scientists in a lot of cases. So bringing them together and making sure that whatever we were building was actually going to accomplish the science. So that's what I started out with. I started in astrophysics, and that really set the foundation for what I decided to go on to in graduate school. Before entering JPL, I really wasn't interested in grad school at all. So kind of getting introduced to cosmology early on at JPL encouraged me to go back to school. But before I had the opportunity to do that, I did work for OPALS Optical Payload for Lasercom Science, and I got the opportunity to do management, which was kind of unique for someone with as small amount of experience as I had, almost none, to work with the highest levels of management at JPL to get this project done. And so OPALS was a payload that went on the International Space Station and beamed down a video using optical communication by basically switching a laser on and off. It was pretty exciting because we had to work with NASA, Johnson Space Center, Kennedy Space Center, and SpaceX also, who launched us. I actually stopped working at JPL before OPALS was done. I took a year off to apply to grad school and ski so that I was ready to start grad school. So I wanted to talk a little bit about why I ended up going into what I did with grad school. I had a lot of time to think about it and figure out exactly what I wanted to study. I'm mostly motivated by questions that I find are interesting and important. And to me, there's nothing more important than trying to figure out what the universe is made of. So that's really what made me decide I wanted to go back to school, is try to learn and contribute to understanding what makes up our universe. But I'm no theorist. I don't enjoy doing homework very much. I like building things. And so instrumentation was a way that I could contribute to cosmology without necessarily writing out the equations to describe what the possibilities were. So bringing hardware and software together to create something, to then measure things, to contribute to science is where I find the most satisfaction day to day. And then my introduction to management when I was at JPL made me realize that I really like being a part of the conversations about the decisions that are made at the project level. So determining what it is we want to do. I wanted to be in the room. I wanted to be a part of making those decisions. So I'd like to stay in management as much as I can so I can keep being part of the big picture. So luckily, ProtoDESI came along, and I was able to bring all of these things together. So now I'm going to talk about the science a little bit, not a whole lot, and I'm happy to answer questions about this afterwards. I just want to set the stage for what DESI and ProtoDESI are supposed to do. So I might go through this a bit quickly. There's a lot. What is dark energy? It's a big question, but it was found within all of our lifetimes that the universe is not only just expanding, but it's accelerating in that expansion. And most of the universe is made up of stuff we don't understand. Now, I'm not going to talk as much about dark matter, which is different than dark energy because it gravitationally it has gravitational properties. Dark energy we really know very little about. As I mentioned, this was first discovered within our lifetime, about less than 20 years ago, using Type 1a supernova. And one of the teams was Saul Perlmutter's team, and they were looking at the redshift of supernova, and they thought that the universe was just expanding at a constant rate. And so it was a big surprise when their their hypothesis was incorrect. It's kind of one of the most exciting things I think that can happen in science when your hypothesis is incorrect and really backed up with excellent data. So now we know that the universe is accelerating, and that leads us to really have to grapple with both Einstein's general relativity and the composition of the universe. So hours and hours could be spent talking about general relativity, but I just want to point out that this extremely successful theory only exists because Einstein had to put in this constant, and he didn't know what it was physically, and it bothered him a lot, and he thought it was unphysical, and it turns out that the equations don't work without it. So for a long time, just stood that way. We have to have this constant, this cosmological constant, in the equations of general relativity to make them work, but we don't know what it is. Now we're starting to wonder, maybe it's dark energy. Maybe that cosmological constant is this big, massive energy in the universe. But we don't know that for sure. We don't know if dark energy is constant. It might change with time. And so that's one of the main goals of current studies right now, is trying to understand, has dark energy always been the same amount in the same form, or does it change over time? Well, how do we explore this? There are a set of equations that can be derived from general relativity, one being Friedmann's equation, in which he breaks up all of the different components of energy in the universe. We have matter.
It's the green line.
Perfect, yeah, okay. Matter, radiation, this is the cosmological constant, maybe dark energy, and K is a geometrical term. Not going to talk too much about it here, but these are the main elements that could make up the universe. So how much of each one of them is in the universe, and then that adds up to telling us how much it accelerates. And I'll get back to what this means in a little bit. So we need to figure out how much energy is in which one of these forms. Each one of these terms is really a density term. and you can reparameterize it to be this W, which is pressure over density. Okay, and if W is -1, then dark energy is a cosmological constant. Did I just go through a whole bunch of cosmology really quick? Yes, but the only reason is because I want these graphs to make a little bit of sense. What we're trying to figure out is dark energy static? W0 here. If it's -1 and doesn't change, this is the evolution, then dark energy is a cosmological constant. That's what we're trying to figure out. So this group of people, just in the past decade, Dark Energy Task Force, they got together and asked, how do we evaluate whether or not we are actually constraining dark energy any better than anyone else? So they came up with this figure of merit. They said, we are trying to measure W as it is now versus as it is in the past. So that's W0 over WA. And that's what we're trying to constrain. And when we understand that, we will have a good idea of whether or not dark energy actually changes with time. They also said, if we're able to make these measurements with more than one probe, more than one kind of way to make the measurements, then our error bars go down. So that's exactly what this graph is. This is the measurements made with supernova, measurements made with baryon acoustic oscillations, and this is CMB. Instead of being W and WA, this is actually the density of the cosmological constant, and this is the density of matter, but it's a corollary to this graph right here. So the motivation here is, if we want to understand dark energy, identify first if it's a cosmological constant or if Einstein's equations are wrong, which is unlikely but possible. We want to measure it in as many ways as possible. And right now, the three leading ways to constrain dark energy are type 1a supernova, weak lensing, which is looking at galaxies through clumps of dark matter and kind of squeezes them around a little bit, and baryon acoustic oscillations. I'm going to talk about baryon acoustic oscillations today instead of the other two. I don't know much about weak lensing. I'd be happy to talk about type 1a supernova later on. But the reason I want to talk about baryon acoustic oscillations is because that's the way DESI is going to constrain dark energy. Okay, so before we can get there, we need to talk about how we make these measurements at all. How do we go from looking at stars and galaxies, etc., to coming up with what is W, which I just made up. I could have made that up, right? Who knows? Well, we do that by measuring redshifts, number one, and then number two, the distances of objects away from us. So redshift is very similar. There's a corollary to the Doppler effect. You know, when a car goes by you, there's that zoom sound. So as it comes closer to you, the sound waves are piling up, and as it moves away, the sound waves are pulling apart. The wavelengths are growing. They are redshifting in a way. Redshifting only makes sense when we're thinking about light and optical, but it's a term that saying the wavelengths are getting bigger. So that's essentially what happens. When objects are moving away from us, the wavelengths get bigger, get larger. Okay, so we can measure when we measure an object's redshift, we're really measuring how quickly is it moving away from us. Now, how do we measure redshift? Well, we know that stars shine light at us, but they also, the light has specific frequencies, specific wavelengths that are determined by what they're made up of, usually hydrogen, helium, things like this. And so we know what the spectrum of hydrogen is, and so we look at the spectra coming from a galaxy, and we say, that looks like hydrogen, but it shifted over. Okay, well, that's how much it shifts. That shift is the redshift. Okay, if you were to look at hydrogen in the lab here and then compare it to the hydrogen you're seeing in a star, you can very accurately determine how much it's redshifted. So that's how we discover the redshift. That's how we figure out how quickly things are moving away from us. Now, Hubble, many, many years ago, said, well, the distance something is away from us is proportional to its velocity. And very close to the Earth, that's actually true. So this right here is Hubble's law. So it's saying, actually, how quickly things are moving away is proportionally dependent on how far away they are. Yeah, well, now that things are accelerating, that's not true anymore. So actually, h naught, which is Hubble's constant, is now time dependent and space dependent. Okay, so we don't know exactly where something is based on its redshift. So we need another way to measure the location of something in space besides just its redshift. And so we use standard candles or standard rulers for this. Type 1a supernova is a standard candle. If you have a candle sitting here and you see how bright it is, and then you put it at the other end of the room, and you see it's dimmed down by a certain amount, you can infer its distance away from you. That's what they did with Type 1a supernova. It's actually a very simple idea. They knew that Type 1a supernova are the same brightness no matter where they are. This is more or less true. But at the time it was true enough. So they knew that wherever they were looking at a supernova, they could compare them to one another and figure out their distances from Earth or from the observer, which is us. Okay, so Type 1a supernova was a way that we could accurately determine how far away a supernova was from us, and then we could compare that distance to its velocity from the redshift and discover that there was acceleration. Another way you can do this is the standard ruler. If I have a ruler here and then move it away, the angular distance will tell us how far away from us it is. So, like I said, Type 1a supernova is a standard candle. Baryon acoustic oscillations are a standard ruler. I'll make one aside here. Type 1a supernova are quite good standard candles, but there's a lot of astrophysics that are involved with supernova. And so there are some differences from supernova to supernova, which make them not exactly perfect standard candles. So there's a lot of work being done now to try to figure out what does cause differences between different supernova. But it kind of is putting Type 1a supernova as not the leading method in cosmology right now. Baryon acoustic oscillations is because it has more to do with fundamental physics than astrophysics, meaning we can trace it back to fundamental equations rather than astrophysics at all. Okay, so what is baryon acoustic oscillations? In the early universe, there were quantum fluctuations, and then these quantum fluctuations grew through inflation. This is very much like throwing a pebble in a pond. You are making some kind of disruption on the surface of the pond, and it waves out from there. You get concentric circles around the disturbance on the pond's surface. The same thing happened, more or less, though in 3D space, where there was a disturbance, and then it moved out from there. At some point, light and matter, light being photons, matter being baryons that make us up, and stars and galaxies and such, separated from each other. So then we have the cosmic microwave background, and then we have matter, and they have this structure built in now because of that kind of ripple effect, the acoustic wave that moved out from the fundamental quantum disruption. So now if we were to zoom way out in the universe, galaxies would not be distributed randomly. There would actually be some order to them. And it is more likely to find galaxies at a certain separation than another separation. This picture explains it a lot better than I can with my hand. It's a lot more likely to find galaxies separated by this radius than by that radius. Much more common. Okay, so this radius is a standard ruler. Now we can't just, say, oh, well, that galaxy and that galaxy, they're that far away. It doesn't quite work that easily. You need to use statistics, and so what you do is you kind of find all the galaxies, say how likely is it to find one this far or this far or this far away from a certain galaxy. So you kind of do a statistical analysis of how likely it is to find another galaxy close to it, and you get a very prominent peak. Okay, there are going to be some galaxies mixed in other places, but there is a prominent correlation between where one galaxy is and its nearest neighbor, let's say. Okay, so this right here, this peak right here, is our standard ruler. So if we know what the separation of the galaxies had to be in the early universe, which we do because we can trace it from that quantum fluctuation through inflation and then to the time of separation between light and matter, we know the separation of the galaxies should have been then. So now if we measure the separation now, we can get a measure of the acceleration of the universe. So this is our standard ruler. Okay, now I'm going to get into the hardware stuff. That was a very fast introduction to all of cosmology, and I apologize, maybe I just confused more than clarified. But the point of DESI is to measure baryon acoustic oscillations. And then from there, understand the properties and time evolution of dark energy. So the way we're going to do it is measure the spectra of 40 million galaxies and quasars, active galactic nuclei. We expect to integrate it in 2018. Collaboration's pretty big. It's a large project, more than 200 participants across the world. So what DESI is a ground-based instrument that will go on the Kitt Peak Mountain on the Male 4-meter telescope. It will have 10 spectrographs with 3 detectors for each one of those spectrographs. And then it will have 5,000 optical fibers attached to little robots so that we can reconfigure the focal plane in less than 3 minutes. So what we'll do is we'll take a picture, basically, or really the spectra of 5,000 galaxies at one time, and then move them all and take another 5,000 galaxy spectra. It's a huge leap from its predecessor, which was BOSS, and BOSS had 1,000 fibers. The reason we have robots is because BOSS had plates that they plugged individual fibers in. They actually had people that would populate, I think maybe up to 5 plates a night by hand. Okay, so 1,000 different fibers into metal plates a couple times a night. Well, you can't do that with 5,000. They said, we're not going to do it. So we had to come up with a new way, and those are little robots. So we have 5,000 little robots looking at galaxies. So it's a very cool project, I think. I'm biased. But DESI is going to be able to look across a huge redshift band from 0, where we are, to more than 4, looking at quasars. So mostly in here, these are galaxies, and then once we get past a certain redshift, we'll be mostly looking at quasars, which are super bright, active galactic nuclei. And we'll measure the spectra for each one of those targets. We can really then make a 3D map of the universe, which is going to be, well, at least out to redshift 4, which will be incredible. And then once you have this large-scale 3D map, you can measure baryon acoustic oscillations, that standard ruler. And we'll have a much better measurement of the acceleration of the universe, and hence dark energy. Okay, so this is what it looks like in block form. The light will bounce off the primary mirror, which is 4 meters, and it will go through a corrector. This are just big lenses that help take out any atmospheric distortions or any distortions in the telescope or camera. So this huge corrector in front of the focal plate, which has all of the positioners. So each one of these kind of pie slices has 500 positioners in them, and each one goes to an individual spectrograph. But the light comes through the corrector into the optical fiber, and then down 50 meters of fiber cable to the basement. And then that light gets spread out across 3 detectors in a spectrograph. So this is the telescope up at Kitt Peak. It's huge. It's 15 stories high. It's just kind of one of the last of its kind, an equatorial mount telescope. It does have a twin in Chile, the Blanco telescope, which is almost identical to this telescope. But this is where DESI will be right here. The mirror is right here. So when this is open, the sky would be there. The light comes down, hits the telescope there, and then bounces up. This would be the corrector, and then DESI will sit on the end of it there. Then they'll have a fiber cable coming all the way down and into a room over here. So why did they pick this 4-meter telescope? Why didn't they pick a 10-meter telescope, let's say? Well, 10-meter telescopes are wonderful, but you can't usually get one all to yourself. So the 10-meter telescopes, let's say on Mauna Kea in Hawaii, like Keck, have multiple instruments with a whole bunch of different teams that want to use that time. It's very hard to take all of the time of a 10-meter class telescope. So the team, long before I was ever on there, wanted to get as big of a telescope as they could, but take all of its time. And so they were able to do that with the male 4-meter. So once DESI goes onto this telescope, DESI will be the only instrument on the telescope. Right. Okay, and so here's a spectrograph. I'm going to go into this in a little bit of detail because there isn't one on ProtoDESI, so this is our last chance to talk about it. But 2 main things I want to point out with spectrographs. Spectrographs are used to measure the spectra of the light, obviously, so you need to spread out the light like a prism. So 2 of the things that went into designing the DESI spectrograph is what wavelength range do we want? And because we want a wide wavelength range, we don't just want optical wavelengths, we want to go into the infrared. We need different detectors that are sensitive at different wavelengths so that we get the best throughput at all of the wavelengths. So that's why there are 3 different detectors. And then the other major element of any spectrograph is what is the resolution? How finely do you want to chop up the light? You could think, why don't you just chop it up as finely as you can? Well, the more chopping you do, the more space you need on the detector. Okay, so it becomes expensive and also becomes very difficult to do all the data analysis. So you kind of only want the resolution up to a point where you need it, and you also don't want to get confused by noise. So there's a lot of back and forth deciding on what is the exact resolution you want, but it's usually determined by what features are you trying to find in your data. One of the main features that DESI is looking for is oxygen 2 doublet. This is something that you can track over a wide wavelength range. So you can imagine you have a line in your spectra that when it's redshifted, when you're looking at it at redshift of 3, it falls off the detector, meaning it's redshifted so much you can't sense it anymore, you don't see it. So you need something that will stay on your detector through a wide wavelength range so you can compare something that's at redshift 1/2 versus redshift 3 or 4. So O2 is one of the main things they'll be looking and tracking through all of the data, and so they need enough resolution to be able to see these. And so DESI is a fairly high resolution spectrograph. So these are the two main things. And again, ProtoDESI doesn't have any spectrographs, but of course this is the heart and soul of DESI. That's where we get the data. Okay, well these are the robots, and the robots are very cool. The robots each can have the fiber, which is right here. So this is the optical fiber. It's 100 microns, so a couple hairs, not just one hair, but a couple hairs put together. And then it is attached to the front of the positioner. Now, this fiber can be moved around anywhere within a 12 millimeter diameter circle. And it does that with two different motors, as they call a theta motor and a phi motor. Okay, so this is where the fiber would be, and then it can move anywhere in a 12 millimeter disk, essentially, or circle. Okay, this is where I want to see if the videos will play. Oh, yes, okay. So this, so there's the fiber connected to the end there. And so what will happen is software will go out and tell 5,000 of them all at once, go to these different positions, and all 5,000 of them will move at the same time. Now they actually overlap on DESI, not on ProtoDESI, so there's extra software to make sure they don't bump into each other. But it's pretty fun to watch them move. So they calculate what kind of moves they need to make to get it exactly where it is. Okay. Now here's a picture of kind of what it might look like with all of them together. Now this is just 500 instead of 5,000. But they kind of, you can see they have to avoid each other. So the algorithm for making sure they don't hit each other is quite complex. But still, it can be reconfigured within 3 minutes, all 5,000 of them. They are allowed 3 tries. They'll move and then say, okay, I'm in my place, and they're allowed 3 tries to get it right. And I'll explain how that happens in a minute, but they're extremely precise. So this is one of the pedals I showed. There's 10 pedals. Each pedal has 500 positioners in them. They screw in, and then the back end has the fiber going to the fiber cable, and then all the electronics that run the actual motors. Oh, something still. Okay, there we go. Oops. Excuse me. Okay, so I said they get 3 tries. Well, how do they know if they're in the right place? We don't trust them completely to end up exactly where we told them to end up, because we need them to be on a galaxy within 5 microns. It's a very small amount. So they have to hit it extremely precisely. So they get a little extra help from something called the fiber view camera. So this is the telescope. This is where the primary mirror is right here, and this is where the instrument is. So there's the corrector and then the focal plate there. Well, there's a camera down here staring at all the fibers. And there are points of light on the focal plate that don't move. They're called fiducials, and they just stay in one place. And so the fiber view camera looks at the whole scene, measures the centroids of all 5,000 fibers, and compares them relative to the points that don't move. And this can be measured within millipixels on the CCD. So we know very precisely where the positioners ended up. And so there is then a control loop that says, well, here's where the positioners ended up. The software evaluates that and says, yeah, not close enough, sends delta commands to the positioners, and then they get 3 tries so that all of them are within 5 microns of where they were commanded to go. Fiber view camera is something that was part of ProtoDESI, so I'll explain how that works a little bit more. Okay, so we are now at ProtoDESI. Okay, so ProtoDESI is just a subset of DESI components, like a prototype, kind of clear from the name. And it was mounted on the same telescope that DESI is going on the 4-meter telescope at Kitt Peak, from mid-August to the end of September. And the purpose of ProtoDESI was to reduce some major technical risks for DESI. So putting fibers on objects was something that theoretically was possible, but everyone was a little nervous whether or not we could pull it off. So ProtoDESI was put in place to reduce some of these technical risks for the DESI project and make sure that indeed when they build 5,000 of these, it'll work. So before they built 5,000 of them, we sent just a handful of them up to the mountain. And we wanted to show that, yes, indeed, we could put positioners on targets relative to guide stars, and then make sure that the telescope stays on guide stars for the duration of a DESI integration time, which is about 20 minutes. So when DESI goes on, it will stare at galaxies for about 20 minutes, which is the amount of time it needs to get all the light down the fibers, so it can identify the spectra of different galaxies. So we wanted to make sure that we could stay on these stars for that amount of time. So these are just some cool pictures that were taken of DESI before it got shipped off. This is the backside of it. Each one of these colorful strands coming off the back is the cord for the electronics to the positioners and the fiducials. And then they get plugged into a board here, which sends the power and the signals for each one of those positioners. This is a laser. And so one thing I didn't mention with the fiber view camera is we're looking at these positioners, but how do we know where they are? How do we centroid on positioners looking from the front? Well, we actually backlight them. We sent light from the back of the fibers straight towards the fiber view camera, and that's what's centroided on. So you need to back illuminate the fibers so we can figure out where they are. So this laser feeds into here. All of the fibers go into this little block here, and so they can either be backlit or they can be imaged by this camera. So the fibers are either backlit so the fiber view camera at the other end of the telescope can see them, or we turn off the illuminator and we image whatever's coming down the fibers on the camera. And this is the front of it. There are just a handful of positioners. We only ended up with 3. One of them broke. And then there's a camera and a couple other things that I think you can see on another image better. Okay, so DESI, ProtoDESI mostly had DESI subsystems, meaning we were trying to replicate everything that we could off of DESI. The telescope was the same. The guiding camera was the same. So this is on front, and this is what we use to make sure we're staying on the stars we want to. The fiber view camera is a 600 millimeter lens. It's like this big. It's enormous. We use the same one that will be used for DESI. The fiducials were the same, and the fiducials are the points of light that don't move. Those are the points of light that help us make sure that the positioners are going to the right place. Those are the exact same ones that will be used for DESI. The positioners are the same ones that will be used for DESI. So we really were trying to test as much of the DESI hardware as we could. And then critical component was integration of software and hardware, making sure that everything worked together. And while you always know this will eventually happen, if anyone's worked with instrumentation, you know it's the hardest part. Actually making the software and the hardware work together in a seamless way is always possible, but very time consuming. So we wanted to get a lot of this out of the way before DESI had to deal with it. Okay, but ProtoDESI didn't have everything that DESI will have. It didn't have a spectrograph. we didn't have one that was ready, so instead we used a fiber photometry camera. We didn't have the DESI corrector, which ended up being okay because ProtoDESI was just a small part of the field of view. And we didn't have a 50-meter cable. So ProtoDESI was all compacted into something about this size and was able to be put on the back of the telescope. So we didn't need anything coming down the telescope. Now, like I said, we didn't have a spectrograph, but we had a photometry camera. And that's what I'm talking about here. This is the block where the fibers go in, so they can either be backlit or imaged here. So we would know when we were looking at a star. We couldn't break up the light, but at least we'd get a picture. We would know that light was coming down. And that's really what we wanted to prove, that we could take a positioner and put it on a star, and light would come down it. Okay. And this is the focal plate. It is not the same as the DESI focal plate because that has room for 5,000 positioners, but it was much smaller. Here's another view of it. Like I said, we were able to put all of it on just one box. This is the front, and so most of these things are fiducial, so not moving points of light. And then we had a couple positioners, and the guide focus and alignment camera was right in the middle.
How big are those boxes on the side, let's say?
Oh, this big. Meter. Is that about a meter? Yeah. And then about that thick, I want to say. Yeah. Okay, so how did this thing work? Okay, so this is a view that we would see from the telescope. And so this is what ProtoDESI was looking at. What we would do is we would pick a field in the sky and identify a handful of bright stars, anywhere from 8 magnitude, which is super bright for a 4-meter telescope, to 15 magnitude. It gets dimmer as you get bigger. Yeah. So we wanted to identify some bright stars and then identify guide stars as well that were close to where the positioners were. Okay, so we identified our field, and then we told the fibers to move to those locations, and then we would iterate with the fiber view camera. Now, how did we know to go to those locations from star positions? There's a special software called PlateMaker. And what PlateMaker does is it takes RA deck positions of stars and turns them into XY positions on the focal plane. It also turns it into pixel space on the fiber view camera and pixel space on the GFA. So it had to take care of a lot of things. It had to go from stars to every one of the components on ProtoDESI. And then it would send those to the guide camera, fiber view camera, and the positioners. They would all move to their respective places, and then we'd hit go, and we'd see, okay, are the positioners in the right place? Well, they would have to move a little bit until we were exactly in the right place. Then we would shut off the backlight LED, and as we're guiding on the guide stars, we would stare at these stars and see if we got light down them. That was it. It's fairly simple, meaning there wasn't a lot that we were trying to achieve, but that's it. Took quite a bit of time to get to that point. I'll explain some of the things that we got tangled up with. So again, the main parts were, can we stare at these guide stars for long enough to get light down them? And can we get the positioners on the stars and keep them there long enough to get light down? Like 20 minutes, so that we can get all the photons we need to get a good spectra. So that was the main idea about around ProtoDESI. If we were able to do that, we would decrease a ton of technical risk. And we gave ourselves a decent amount of time to do it. So these are some pictures of us putting ProtoDESI on the telescope. There it is, so you get an idea of how big it is compared to a person. And this is it in the back of the telescope. That's it right there. It only took us about an hour to put it in. We thought it would be a much bigger deal, but they just cinched it up and screwed it in, and then we were ready to go. So very quickly, we were able to turn everything on, and start doing accuracy tests. Now, accuracy test is just a test of the fiber view camera and the positioners. We wanted to see within 3 moves how well would it move to its place. Not looking at stars, just independent of that. And so we started doing these positioner tests, trying to see, can we get to a commanded position within 3 moves in 5 microns of the expected position. We found that we couldn't right at first. We had a lot of trouble getting this accuracy. Even though we had seen it in the lab at LBL, we couldn't get it to work on the telescope. And it turned out it was because there was a fan on in the dome. Every little thing, every air, every fan or air current in the dome could mess up these measurements. It's that accurate. It needs to be that accurate. So we had to turn off all the fans. We actually had to open the dome so that the temperature was even throughout the whole thing. And this has actually changed a bit of the DESI plans, because they were hoping to do a bunch of calibrations earlier in the day with the dome closed, and now I find they cannot. You actually need these conditions. You need it to be open. Okay, so did accuracy tests, and then we were able to take an image with the guiding camera, and so then we were able to confirm that we could guide on stars, meaning the camera would send correction signals to the telescope, so the telescope would be moved by the instrument to make sure it stayed on the stars. And then August 30th, so not quite a month, but about 2 or 3 weeks after we got on, we were able to go through a full sequence, meaning go through this whole process here. And we didn't get light down that time. We went through the process. We said, okay, here are the positioners. We would move the positioners to where they were supposed to be. We would check with the fiber view camera, turn off the lights, and there was no light coming down the fibers. So we thought we were moving to where we were supposed to, but we weren't. This has mostly to do with astrometry, meaning you need to know exactly where those stars are. You need to know the RA index of those stars relative to the RA index of the guider stars very, very well. And I don't know if you guys have heard, but recently a data set came out from Gaia, which is doing a big survey of stars and star locations. And so we were using an old catalog of stars, and it was just old enough that we actually need this brand new catalog, this Gaia catalog. So it came right in the nick of time. So we needed to know exactly where the stars were with incredible accuracy in order to actually get the fibers on the stars. So it took us a couple more weeks trying to work all this out to eventually get light down the fibers. Then we had a couple weeks of doing some tests, figuring out how well were we pointing, and then we took it off at the end of September. So a whirlwind of a month and a half, really. But we did get first light. This is an image with the guide camera. This is M2. We certainly weren't guiding on anything this bright or this dense, but we wanted to make sure we could see something we recognized, and it was very beautiful. And then when we got first light down the fibers, there was a lot of jumping up and down because it had been over a month for us trying to get this to work. That finally did. And all it was 3 dots. This is the photometry camera image where the light from the fibers gets fed into a camera. And so what we were seeing was the starlight going through and actually landing on the camera finally. You can see this is one of the monitors there. You barely see a point of light there. So we were sitting there staring, waiting for the exposure to be done, and then it came up, and it was a glorious moment. Okay, so I'm going to bounce now from overview of ProtoDESI into some of the results. So this just ended about 3 weeks ago. So we're still milling through some of the results, but we're trying to evaluate how well we did. So with guiding, we were trying to figure out how well can we guide over a 20-minute exposure. So we certainly can guide. We can guide pretty well, but we discovered we can't guide good enough for DESI. we need an error, an RMS error of 30 milli-arc seconds. And our RMS error is 10 times that. So we're guiding, but again, not good enough. Now this probably has to do with the signal to noise of the camera. So one nice thing about working on something like ProtoDESI is it's never a failure, because anything that fails just gets fed back to the instrument. And so it's a success in that you identified a problem before it came up on DESI. So we were successful in finding that the guider didn't work that well, because now we know that we need to put some more time and effort into this camera to make sure that we guide more effectively for DESI. So again, we were able to guide on a range of brightness of stars, but we're not quite at the accuracy we need to. This image here is once we take a full image with the guiding camera, and then it says, there's the star we're going to guide on, and it shrinks the image down just so that the readout time is less. And then we just have these postage stamps of the guiding star, and then it uses that set to send the correction signals to the telescope. So that's what these are. These are the correction signals. It needs to be at 0. That's where it's supposed to be, and if it's a little bit off, the guider tells the telescope, move the telescope this much, or move the telescope that much. So that's what the guiding signal is supposed to be doing. Okay, I talked about the accuracy tests a bit. We need the positioners to be able to point within 5 microns. So I said we weren't able to get the accuracy for a long time that we expected, but eventually we were able to. And so this has an average error of 2.7 microns. So we were able to get the positioner right on point within 2.7 microns. So this right here is we just told the positioner to move in a grid, and then we measured the centroid with the fiber view camera. And so we were able to, over a grid, what is its error? And so less than 3 microns. After 3 submoves. So that was the requirement, that on the first move, it doesn't have to make it. By the 3rd move, it has to make it. So we were able to show that we could achieve that. Okay, and then this is the heart of the results for ProtoDESI. How well could we point at a star? So this image on the right here is a dither pattern. We would move the positioner to exactly where it was told to go and take an exposure there, and then we would move the positioner in steps around that place to see if actually the maximum of light was somewhere a little bit further away from exactly where we were. So it turns out that the maximum value was about a micron away from where we were pointed. I'm sorry, an arc second. Micron would be pretty good. It was about an arc second away from where we should be, which corresponds to half of a fiber. So we were about half a fiber off from the maximum. This probably isn't good enough, and we don't understand why it happened quite yet. It could be that some of the focal plate was out of focus, so it was a little tilted. So that might be one of the reasons. But it might also be that there's some issue with the software telling it where to go. Maybe it's not telling it where it's supposed to be going. But what we found is that it's not hitting it right on. It was hitting it right on enough that we could see light through it, but we weren't at the center of the star. We also wanted to measure its how well it stayed on the star over 20 minutes. And there's quite a bit of variation here. Each one of these, we had 3 different positioners, and you can see that the throughput is actually quite different for each one of them. That's okay. That makes a little bit of sense. But there's quite a bit of jitter, more than we expected, meaning if you're staring at a star for 20 minutes, the flux should be the same. The star's not moving around. And if the positioner's not moving around, why would the flux be changing? There could be atmospheric issues there. but we think it's in part because it was not looking at the center of the star, it was off on the side, and so atmospheric effects could make more of a difference in the flux coming down the fiber. So we've got a set of data that we're still working through and trying to understand whether or not more changes besides those for the guider need to be made for DESI. Okay, I mentioned a couple of the problems we had on the mountain. A couple others are the GFA, that's the guiding camera, was extremely fresh, meaning they finished it and sent it to us from Spain. They hadn't really tested the camera at all. So the likelihood of it working was pretty small. It did work, which was great, but there were many times that I had to get into the telescope, kind of wrap my body around like this, and solder it back together in the middle of the night. So I think one thing we learned is you shouldn't take a camera or an item that isn't a little bit more tested than what we had. And the reason we accepted it was because we wanted to get on with it and we had limited time on the telescope. We were lucky that it worked. And the weather, so Tucson is where Kitt Peak is, has good weather most of the time, although in the summer they get a lot of rains. That's why we got the time, because nobody else wanted to use it. And we got pretty lucky with the time. The weather was actually quite good until the very end, which is the time we needed it most. When we were trying to determine how well we were pointing, we wanted really clear skies, and we didn't get them. So our data set is smaller than we wanted, but we had to get off the telescope. And then the astrometry was another challenge, trying to make sure we could get the positioners on the fibers. We needed really good astrometry on the guider and stars and the target stars. These are just a couple of the challenges that faced us. Again, as I mentioned, when you bring hardware and software together for the first time, there's a lot of debugging, but those are usually problems that can be solved within a day or so. So in conclusion, ProtoDESI was really a great success. First, because we were able to get light down the fibers. We showed this will work for DESI. This is not a crazy plan. There are some improvements that need to be made, but we were able to identify them early before we go into full production of DESI, which is starting just around the corner. A lot of the work from ProtoDESI is going to go into commissioning of the DESI instrument, and hopefully it will reduce the amount of time needed to commission the instrument. Commissioning is usually that amount of time for an instrument that is spent before you get science data. It's just trying to make the whole thing work. And so the amount of time it's on the telescope not taking science data, you want to minimize that as much as possible. As I said, the positioners were consistently about an arc second off from where they're commanded. So this is a lingering question that I will be working on for the next couple months. And now, as I said, we're ramping up to build DESI. So DESI, keep your eyes open for information about it, because it's really a one-of-a-kind instrument with 5,000 robots on it. It's going to be quite a thing. Anyways, thank you so much. I have to say thanks to the ProtoDESI team, because we couldn't have done it without a big team coming together, and I got to learn a lot from all these super experienced instrument people and scientists. And then thank you for inviting me to this talk. This was exciting.
It's 5. Some of our students have classes they have to go to. Move quickly and quietly. The rest of us will stay by for the 15-minute questions and answer session. Take this outside. I forgot to say. Yeah, take it outside. All right, and we'll begin with questions now. Parker, yes.
So what's the schedule for DESI?
So I believe it's sometime in 2018, maybe 2019. It's supposed to go on the telescope. So they are starting to mass produce positioners and fiber. Now they finished the first spectrograph. So within a year, I think they have planned for building most of the focal plate. So they'll need a big chunk of the positioners done, and then they can start assembling everything. So it's mostly on track for 2018 commissioning phase. Yeah.
Sort of a general question. Suppose it all works, can you review the time span to take data after DESI works? 5 years, you said?
5 years, that's right, yeah. And so there's a lot of work going on right now to identify what we want to look at. So there's a lot of imaging surveys identifying the galaxies we will eventually look at with the fibers. And so then there will be a scheduling effort after we have all this imaging data to figure out the list of galaxies, what time of year it makes sense to look at them from, Kip Peak, and then we'll probably go back and look at things a couple times in some instances.
Go back, and you're looking for changes in the Z value?
Not changes at this point. No, really we're just almost in a way making a catalog of redshifts across a large range of redshifts so that we can create a 3D map, basically, of all of these galaxies. Yeah.
At the end of the 5 years, you plan to move it to Blanco telescope to the other part of the sky?
That's a good question. I'm certainly not involved in those discussions at that level. There's some talk about building something for Keck, maybe, that looks something like this. And really, it's all going to hinge on what happens with LSST, I think. There's going to be so many objects that LSST is able to identify. What's the follow-on to that going to be? And so maybe the need will be something different than Ceratololo DESI. But yeah. Yes?
Do you have a slide of the 500 sensors attached to the plate?
Oh. No. The best I can do is this. So each one of these 10 is has 500 of them on it. But
I guess my question is, what attaches to what? I think several years ago we had someone here that actually had some of those plates with the holes.
oh yeah.
in them.
Mm-hmm.
Yeah, and that's like, well, obviously once you drill the holes, you can't use the plating. So
Yeah.
what attaches to what on your thing so you can move it and not have a distortion later on?
Yeah, so this is what it will be attached to. So this right here, it's kind of like a, well, it screws in like a car, something like a spark plug. Okay, so it's all screwed into this metal plate here, and then off the back the fibers come off, and they are controlled elsewhere. So they're actually then coiled all the way down. Now you can't take this apart, really. It would be a real pain in the butt to take it apart. So unlike BOSS, where they could just pull out the fibers and have these really cool metal discs, you can't take these apart. You don't have to, because you can turn them into something new really quick. But the fibers will always be attached to the positioners. Does that kind of answer your question a little bit?
And then I had one other quick question. The standard ruler you talked about before as a radius, is that a galaxy clusters that you were talking about?
It doesn't necessarily have to be. No. This is even larger scale than galaxy clusters. This is maybe one step even further out from that. Where just kind of general distribution across the universe, they're bundled. Because you can imagine a galaxy cluster might be all local. Well, they're maybe on one of those kind of circles. You know, the galaxy cluster is part here, but it has a corollary on the other side of the circle. So it's slightly different scales than that. Yeah.
You said you use the Baryon oscillation to determine the acceleration.
Mm-hmm.
So like, how does that play into the dark energy part of this?
Yeah, sure. That's a good question. So we're able to determine the acceleration because we know how big those kind kind of those circles are early on, and then we measure them now. We see how much they've expanded. So then the acceleration helps us understand dark energy because it tells us how much the distribution of matter is changing over time. And it goes back to, well, really can go here, which this is the, we had the Hubble constant before. Well, now it actually depends on time. Okay, so you can think of, this isn't exactly acceleration, but the expansion and the acceleration and expansion of the universe depends on what's inside of it. So these are the energy density elements in the universe that make it accelerate. Now, where does this come from? Einstein. And he kind of figured this out from geometry in a lot of ways. So all it's really saying is if we're seeing the accelerating universe behave in a certain way, we can infer certain things about the components that make up the universe, which tells us whether or not dark energy is exactly this cosmological constant. Maybe it's a mix of some things, and maybe it changed over time.
So is like this dark energy what's causing the acceleration?
Yes, essentially. Yeah. But we don't know what it is, so it's really annoying to scientists. You know, it's kind of incredible to me that we understand only 5% of what makes up our universe. So there's big questions for us to answer.
What's the redshift range that DESI is supposed to cover?
Up to 4 with quasars, up to about 1.7 with galaxies. So slightly different science there. With quasars, you're looking at the Lyman alpha forest. So it's really what light is missing rather than what light do you see. But yeah, up to redshift of 4. Yeah.
Okay, so it's going to go a bit past where the supernovae cut off because they cut off around 2-ish.
That's right, yeah. That's right. And we'll have a lot more data with a lot less systematics. Not that I have no problems with supernova. It's really fun science. But one of the nice things about BAO is there are less systematic errors.
Well, and also it's a totally different way of looking at things, and you want to be able to try to measure acceleration in different ways, as you showed on that.
That's right. Yeah, that's right. Yeah. Yes.
On the termination, or congratulations on getting the first light.
Thank you.
Really exciting. And,
Yeah.
how are the fibers terminated when you get a star down the fibers, or a ball lens? Or
Good question. We on ProtoDESI we have on both sides glass ferrules. Actually, so you slide the fiber in, and then you put some UV curing glue on the end to help them stay inside.
Green lens.
Yeah. For DESI, the front of all of the fibers will have this because this is what you screw into the positioners. So that's how you can hold on to the fiber, these glass ferrules. At the end, they're terminated in a slit for the spectrograph. And I'm not positive whether or not they have those glass ferrules on there or not, or they have another way to hold on to them at that end. But what we did is we put the fibers in these glass ferrules, and then we had a fiber holder where we would just push it in a hole and screw it in kind of just with pressure, holding it there. Yeah.
Can I follow up? A composite slit of the 500 fibers? Is that what it is? Or I mean, some other geometry? There's a couple of spectrographs per
Yeah, there's
per
one
pi wedge?
spectrograph per wedge.
Okay.
And I believe so that's 500 fibers per wedge, and I believe it's one slit per spectrograph. So, and this is actually one of the incredible things about DESI, that these slits are pretty big, as you can imagine, and they're actually winding this thing from the top of DESI down the telescope to the spectrographs. you know, a box about this big, kind of winding around the telescope, because you want there to be some give in the fiber, in that 50 meters of fiber, so it doesn't get stressed at all. I worked on, there's one part of the fiber system that's pretty unique on DESI, where instead of using connectors, we have, at one point, there's two parts of the optical fiber that have to come together, and instead of using connectors, we're splicing them together or melting them together. And so we take these two parts, melt them together, and then wind them down. These are really hard to work with, so it's going to be an incredible task to get that slit head kind of all the way down there. Yeah.
All right, let's thank Parker for really